Okay, so far we've talked about correlation, which is a quantity that can describe a relationship between two numeric variables. And in this section we're going to talk about linear regression. Okay, and so in linear regression, what we're going to do is we're going to try to create a model. Okay, or maybe I should say a mathematical model. To kind of illustrate the relationship Okay, and what I mean by illustrate the relationship between two numeric variables is we're going to create basically an equation. Make an equation for a straight line. And we can use this equation to make predictions. And so whenever we're talking about linear regression, we have an x variable and a y variable. Okay. And we have names for each of these things. And so the x variable is sometimes called the explanatory variable. Or the predictor variable. Or the independent variable. And then we have the, on the y variable, it might be called the response variable, the predicted variable, or the dependent variable. Okay, and the key idea here is we use the x variable to make a prediction about the y variable. Okay, or you can plug in any of these other names. We use the explanatory variable to make a prediction about the response variable. And so, you know, when we create an equation, the equation will be in the form y hat is equal to a, this is the letter a, plus b times x. Okay, y hat means this is our prediction for y, or predicted y. A is our intercept. And b is our slope. And so, for example, so to kind of just give an idea of how this works, let's say we want to look at a book. Okay, and what we're going to do is we will look at the number of pages. Look at the number of pages in the book, and we will use that to make a prediction about how wide the book is. Okay, so just to kind of illustrate what this looks like. This is my illustration of a book. And we're going to look at basically the width of the book. And we're going to look at the number of pages. Okay, so what is our y variable? And what is our x variable? What's our y? Y is the width, okay? And what is x? Pages, the number of pages. Okay, so we're going to predict width based on the number of pages. So we can write predicted width is equal to a plus b times x, which is pages. Or we can also do, I can write width hat is equal to a plus b times pages. The hat over, so if we have this we call y hat, and this just means our prediction for y. Okay, the hat just means it's not y, but it's something related to y. So in this context, the hat means it's our prediction. Later on we'll encounter the hat again when we're talking about p, and we have p hat, which just means it's something related to p but not actually p. Okay, and so so one example is we're going to try to predict the width. So we've got predicted width equal to 6.22 plus 0.0366 times pages. So this is an equation that our equation provided by the book for predicting the width of a book, provided by our textbook, for predicting the width of a book based on the number of pages. And this will provide predicted width in millimeters. Is this okay? Yes, question.
So just to get it clear, the 0.0366, which is actually B, is basically the weight, the wideness.
We'll get to that. Okay, we'll get to that. Okay. So in this case, we have predicted width, which is basically y hat is equal to a plus b times x, okay? So here a is our intercept. What is our intercept here? 6.22. And b is our slope. What is our slope here? 0.0366. Yeah. All right, so let's say a book has 100 pages. Okay, what do we predict its width to be? We predict the width will be, we're going to do 6.22 plus 0.0366 times 100. So our predicted width is 9.88. Okay. Is that good with everybody? All right. Let's say a book has 200 pages. What is the predicted width here? And then we'll say a book has 300 pages. And what is the predicted width in that case? So what do you guys have? 13.54. Okay, so for 200 pages, we have 13.54 millimeters thick. And then for 300 pages, we are at 17.2 millimeters. Is that okay? All right. How much did our prediction change when we went from 9.88 to 13.54? How much did our prediction change when we added 100 pages? When we added 100 pages, our prediction went up basically 3.66 millimeters. Right? Okay. How much did it change from 13.54 to 17.2? From when we went from 200 to 300 pages, it also went up 3.66 millimeters. Okay, so if I said, we have 400 pages, I can get that by doing what?
Adding
I can do 17.2 plus 3.66, and I would get 17.2 plus 3.66, and we would get 20.86 millimeters, right? Everyone's good with this? Okay. Well, this gives us an idea of what the slope means, okay? Where are we getting 3.66? It's our slope times 100, okay? So what this means is that, so what is the slope? The slope is equal to 0.0366. And what this means is that if I increase x by 1, we predict y, or our prediction for y, I'll say if we increase x by 1, our prediction for y goes up by the slope. All right? And so if we increase x by 100, our prediction for the width goes up by 100 times the slope. And that's what we're seeing. If I add 100 pages to a book, our prediction for the width goes up 3.66 millimeters. So I think Ryan said if we increase one page, okay, if we add one page, our prediction for the width goes up 0.0366 millimeters, which is a very small quantity, but that's kind of the idea. Like if you add one page, you know, how much does the width of the book change? It's going to change by a very tiny amount. So we can think of, yeah, maybe the width of one page is 0.0366 millimeters. So if we increase x by 1, our prediction for y goes up by the slope. This is the interpretation of the slope. Okay, does that make sense? Yes, question?
Aside from the intercept and the slope being provided by the book, like how would you find that out?
Yeah, so we'll talk about calculating the slope in a moment, but I think it's more important that we learn what the slope means and the interpretation first. So we'll cover the interpretation and the understanding first, and then we'll talk about how to calculate it, okay? Okay, so here's another example. Okay, so here we're going to try to predict the value of a car based on its age in years. Okay, and so in this case we have predicted value is equal to 21375 minus 1215 times age. Okay, what is our slope in this problem, or in this equation?
1,200.
Our slope is negative. Okay, so our slope is negative 1215. Okay, and what is the interpretation here? If I increase x by 1, my prediction for y changes by the slope. What is x?
Age.
Age. Okay, so what does it mean?
20 years.
Yeah, so if I increase the age of a vehicle by 1, what happens to y? What is our y?
Value goes down.
Yeah, so in the interpretation here is if I increase the age of the vehicle by 1 year, okay, my prediction for its value what happens to its value? It goes down how much? $1,215. I guess I got the dollar sign there. Does that make sense for the interpretation of the slope? If we increase x by 1, we predict y changes by the slope. That's the slope. Okay. Yes?
So A, in this case, was the initial price of the car, right?
Okay, yeah, you're jumping ahead of me again. All right, so in our equation, we also have y hat is equal to a plus bx, okay, or b times x. A here is our intercept. Okay, the intercept is our prediction for y if we can plug in 0 for x. Okay. Sometimes it makes sense to plug in 0 for x, sometimes it does not. Okay, so here we had, earlier we had predicted width of the book, so for the books, we had predicted width is equal to 6.22 plus 0.0366 times pages. Okay, so here our intercept is 6.22. All right, so this is if a book had 0 pages, we predict the width to be 6.22 millimeters. All right, what does that mean? So, I mean, loosely, it could be thought of as, yeah, the thickness of the covers of the book, okay? So if we remove all the pages from this book, all we would be left with is the covers. How thick are the covers together? Maybe 6.22 millimeters, okay? It's a prediction. Again, all of these are predictions. As for the car, we said predicted value, or I could write value hat was equal to 21375 minus 1215 times age. So if the intercept here is 21375, so this says if a car is 0 years old, okay, we predict the value is 21375. So maybe the value of the car when it's new. Okay, but in some cases it doesn't make sense. So let's talk about people. Maybe we say predicted weight is equal to, I don't know, I'm just making up numbers here. Okay, I'm just going to say A plus B times height. Okay, so we're trying to predict someone's weight based on their height. Okay, you cannot have height of 0. Okay, so the intercept is a, whatever value that is. Okay, I don't know what that is. Okay, but this would be our prediction if height was 0. Our predicted weight if height is 0, but you cannot have a person with a height of 0. Okay, so I mean, literally that person does not exist. So, in this case, the intercept does not make sense. Okay. Okay, so that is the interpretation of the intercept and the slope. Okay, and I hope that that's all okay with everybody. All right, I want to talk about kind of the idea of residuals, okay? So let's say, you know, these are our data points, and we have, I don't know, a trend line here, okay? The difference between the vertical distance between an actual data point and the trend line, this is known as the residual. Okay? The difference between the data point and the vertical distance to the trend line which is basically its predicted value, is called a residual. Okay, so the residual is equal to the actual value minus the predicted value for that x. Okay. The trend line is selected to minimize the sum of the squared residuals. And so it turns out, just by you know, some mathematical properties, that the slope and the intercept of the trend line that will minimize the sum of squared residuals. Okay, so you think of these vertical distance to the line and you square them and you add those up. The line that minimizes that, the best fitting line, will always have the same properties. Okay. The best trend line will have the following properties. Okay, the slope, B, will be equal to R. What's R? Thank you. R is correlation. Will be equal to R times Sy divided by Sx. What is S? S is the standard deviation. So Sy is standard deviation of the y variable. And what will Sx be?
The X.
The standard deviation of x, of the x variable. Okay, so the slope will be the correlation times the standard deviation y divided by the standard deviation of x. Okay, and then the intercept is a will equal to y bar. What's y bar? Okay, will be y minus b times x bar. So what's x bar? Mean of x. And what's y bar? Mean of y. Okay. And what's b? The slope. Right? Just right above. So once you figure out the slope, you can use that to figure out the intercept. Okay? And the best fit line will always pass through the point x bar, y bar. Is that okay? Kinda?
Yeah, I'll definitely watch this video again.
So these are just formulas that we can use to calculate the slope and intercept, okay? And we know how to get the mean of x, right? If I gave you a bunch of data points, you would just take the x column and you would take the mean of them, okay? And if we had to, we could get the standard deviation of x also, right? We would just take the values in the x column and find the standard deviation of those values, okay? Same thing with y. We would take the column of y values, take the mean of those y values. We would take the column of y values and we'd take the standard deviation, okay? And we could, if we had to, we could calculate these ourselves. If they're given to us, great, we can just plug them in, okay? Correlation is calculated using a computer, all right? There is a formula, but we didn't learn it. So correlation will be given to you or provided as part of computer output. And then you can plug those in and get the slope and intercept. So it's just a matter of plugging in these variables, okay? You just correctly label what's the standard deviation, what's the mean. And that will give you the slope and intercept, and you fit those together into y hat is equal to a plus b times x, okay? And oftentimes we replace x with the variable that x represents, such as pages or age of the car, and we might replace y hat with what it represents, the predicted width of the book or the predicted value of the car or whatever else we're talking about. Yes, question?
I'm guessing and hoping you can give us an example right now.
I was not planning on doing that. We could, I guess. You're hoping for an example? Sure. So maybe, okay. So maybe we've collected some data here, okay, we're going to try to predict someone's GPA based on the SAT score for math. Okay. And so what we have is, based on the computer output, so the computer says R is equal to 0.194, all right? And then you find the mean SAT score is 649.5 with a standard deviation of SAT scores will be 66.3. The mean GPA is 2.63, and the standard deviation for GPA is 0.580. Okay, so we want to create y hat is equal to a plus b times x. Okay, and I'm going to just throw out formulas. B is r times sy over sx. These are the formulas. And a is y bar minus b times x bar. Okay, so let's solve this. What is our y variable and what's our x variable? The y will be GPA. So GPA is going to be y because this is what we're predicting. And what are we using to make that prediction? SAT score. So SAT score for math will be our x. Okay? So mean SAT, what is this? This is x bar. Okay? Standard deviation of SAT? SX. Okay? Mean GPA? Y bar. And standard deviation GPA? SY. Okay? So it's just a matter of labeling these. R is R. Okay? So what do we have to do? We got to figure out A and we got to figure out B. Okay? Well, to figure out A, it requires that we know B, so we're going to start off with B first. So B is R times SY over SX. So I'm going to plug in 0.194. What's SY? 0.580. And what's S divided by SX, which is 66.3. Okay? So if I do the math here, I'm going to get 0.001697. Okay, it's a little value there. Okay, let's calculate A. A is y bar minus bx bar. I'm just taking in my formula here. What's y bar? 2.63. I'm going to subtract off what's b? 0.001697 times x bar. And what's x bar? 649.5. And so when I do this calculation, I get 2.63 minus 1.102202. And so this kind of rounds off to 1.53. So I'm going to just take these values and plug them in. Okay, so I have y hat is equal to 1.53 plus 0.001697x, or I can write predicted GPA is equal to 1.53 plus 0.001697 times math SAT, whatever that is. Okay? And that's what we have. And we can see the correlation is not very strong between math SAT and GPA, but overall there is maybe a little bit of a positive trend. All right, is that okay? Okay, let me finish with a bunch of warnings about regression. Okay, so number one, make sure, do not use linear regression if the relationship is not linear. How do we tell if a relationship is linear?
Scatter.
Make the scatter plot, right? So you must make a scatter plot. R by itself will not tell you if it is linear. Again, correlation, this is another warning. Correlation is not causation. So correlation might give us insights or clues as to if something is causing the other. Help find cause and effect relationships. But correlation by itself does not mean that there's a cause and effect relationship. Okay. Number 3, beware of outliers. Outliers can really mess things up. Okay, even just one outlier, depending on what it is, right? Let's say you want to see, is there a relationship between shoe size and income? Shoe size versus income. What kind of correlation would we see here? Right, we should see no relationship, right? We're going to see people with small feet making little money and people with small feet making lots of money. We're going to see people with big feet making a little money, people with big feet making lots of money. Okay, so overall, you're going to have R equal to 0. All right? What if in my data set, I suddenly have Shaquille O'Neal? Okay? Shaquille O'Neal has really big feet. Does he also have a lot of money? Or yes, okay, so he would be somewhere out here, okay? High income and big feet, right? And so just this one outlier, so over here we would see no relationship like this. But just this one outlier with Shaq suddenly in it, suddenly affects it like this, okay? He suddenly brings things up. And because he has such big feet and his income is so high, it's going to be, it's going to show overall, we're going to anticipate that bigger feet means higher income, but that's not the case, right? Shaquille O'Neal is an outlier and kind of an exception to that we would expect overall there to be no relationship or a minimal relationship, if any relationship were to exist. Okay? Yes?
Wouldn't be also in the other side other outliers that will balance things out?
Maybe, maybe not. There might be outliers on the other side that balance them out. There might not be. Okay, this is why it's important to look at your data, to create a scatter plot and look at your data to see, are these outliers going to mess things up and throw things off? Okay, so when you have an outlier like this, it might make sense to say, you know what, this is unusual and not getting at what I'm trying to find, so I'm going to remove it, okay? But you shouldn't just arbitrarily remove outliers just because they're inconvenient, but you should say, you know, should I keep this here or not? Okay, and then one more warning, do not extrapolate. Okay, so extrapolate, so that would mean do not make predictions where you have not collected data. Okay, so here's a silly example that we kind of talked about earlier. Let's say you were measuring the height of a child and you're comparing it to age. Okay, so every year you measure the height of this child, and every year the height goes up. Okay, so maybe from ages 3 to age 12, you see the height increasing every single year. Okay, and so it might be tempting to say that by the time the child is 50 years old, that this kid will grow up to be, you know, 25 feet tall and still growing, right? And you know, that's not the case, right? If we try to use this and say, oh, when the kid is when he turns, you know, at age 60, he's going to be, you know, as tall, you know, we can't make predictions out here, right? Okay, because what happens is that as age goes on, suddenly the height levels off, right? So we don't know what's going to happen in the future. We don't know if the trend will continue or not, okay? And so, you know, anytime you see a trend, it might be tempting to say, oh, this trend is going to go on, okay? But, you know, what happens in the future? Maybe it does that. Maybe it continues on. Maybe it goes like this. Maybe it goes like this. Who knows, okay? So as far as the future goes, we don't know what's going to happen, all right? So, you know, it's easy to see the pitfalls when we're talking about trying to predict a kid's height 60 years into the future. But a lot of times you'll see reports saying this has happened for the last 30 years, so in the year 2050, life is going to look like this, which may or may not be true, okay? We can only say that if the current trend continues, and that's a big, big if. That's a big, big if. Okay, I got one more thing for you. Okay, last thing is r squared. This is called the coefficient of determination. Okay, basically for linear regression, we take our r, and if we take correlation and we square it, it turns into big R squared. What this tells us is tells us how much of the variation in y can be explained by the variation in x. All right, so I don't know. Okay, so here's an example. Let's say you know, you create a scatter plot and it's between someone's height and their weight. Okay, so let's say r is 0.6. So that means r squared, if I do 0.6 times 0.6, I would get 0.36. My r squared is 0.36. So this means that, you know, what goes into determining someone's weight? Okay, and there's lots of factors that go into determining someone's weight. One of those factors could be height, okay? But things like diet, you know, their waist size, yeah, there's all sorts of things that go into determining a person's weight, okay? And what this says is from a data perspective, not even saying what causes. There's, again, correlation does not tell us about causation, okay? But what we can say is just from an analytic perspective, about 36% of someone's weight can be matched with or explained by a person's height, okay? 36% of a person's weight can be explained by the person's height. And again, this is not a cause and effect relation, but just knowing someone's height gives us information about the person's weight, but only about 36%, all right? Because there's lots of factors that go into determining someone's weight. Okay, we'll end there. Have a good week, you guys. Stay safe, and we'll see you next week for the quiz.